Okay. Today we'll be revising what you call refraction of light. So I'll complete refraction of light basic theory. We will also complete the sections connected to refraction, critical reflection, total internal reflection. So once we complete these sections, then we just can solve all the questions and we meet next time. We can solve simple harmonic motion as well as what refraction of light questions. Okay, right. So right topic refraction of light. Refraction of light. And what do you mean by refraction? Now, when light travels from one medium to another medium, there will be a change in the path. This change in the path is known as what? Refraction. Okay. So when light travels, for example, if you take when light travels from a denser medium to a rarer medium. So I call this the rarer medium. Rarer medium means speed is large. I call this the denser medium. I call this the denser medium. Here, speed of light is less. Okay? So, rare medium to denser medium, light rays travel. That's the normal. Rarer, denser towards the normal. Rarer, denser towards the normal. This is called angle of incidence. This is called angle of refraction. I is called angle of incidence. Angle of incidence. R is called angle of refraction. Angle of refraction. Okay. Angle of refraction. Okay. Also, if light travels from denser to rare, if light travels from denser to rare, so here you go. This is your denser medium. This is your rare medium. So when light travels from denser medium to rare medium, denser medium to rare medium, it will move away from the normal. It will move away from the normal. Okay. So the change in path of light is known as what? Refraction. When it travels from one medium to another. That's right. That's right. When light travels from one medium to another medium, when light travels from one medium to another medium, there is a change in path. There is a change in the path. There is a change in the path. And this is known as refraction. And this is known as refraction. And this is known as refraction. Okay. Next time, right? When light travels from a rare medium to a denser medium, when light travels from a rare medium to a denser medium, it will move towards the normal. It will move towards the normal. It will move towards the normal. And when it travels from a denser medium to a rare medium, and when it travels from a denser medium to a rare medium, it will move away from the normal. It will move away from the normal. Okay, quickly note this down. Quickly note this down. Okay, right. Now these are the definitions. Absolute refractive index. Absolute refractive index of a medium. Absolute refractive index of a medium. If I write it, speed of light in a vacuum divided by speed of light in a medium. Speed of light in a vacuum. Speed of light in a vacuum divided by speed of light in a medium. Speed of light in a medium. So, for example, absolute refractive index of glass. That is speed of light in vacuum over speed of light in glass. Absolute refractive index of water is going to be C over CW. C over CW. Okay? C over CW. So, absolute refractive index of glass is C over CG. Absolute refractive index of water is C over CW. Okay? So, this is absolute refractive index. Absolute refractive index of glass. This is absolute refractive index of water. Okay, right. Have a look at this. Now let's say medium 1, let's say medium 2. Speed of light in medium 1 is C1, absolute refractive index N1. Speed of light in medium 2 is C2, absolute refractive index is N2. Consider light traveling like this. Now you can write a relationship here. You can write a relationship here. Absolute refractive index is speed of light in vacuum over speed of light in medium. Cross multiply. N1 C1 is equal to C, equation number 1. Look at this. N2 is equal to C over C2. Cross multiply, you get N2 C2 is equal to C. Equation number 2. N2 C2 is equal to C. Now what can you say about equation 1 and equation 2? Equation 1, equation 2, both are what? Same. So equation 1 and equation 2 both are equal. Therefore, you can say N1 C1 equals N2 C2. This is like Boyle's law equation. Therefore, you can say absolute refractive index in the medium into speed of light in the medium, that is equal to constant. There you go. This is one of your theories, important theories. Okay. This is your theory point number 1. That's right. That's right. Consider light traveling from one medium to another. We can build a relationship. Between absolute refractive index and speed of light. As indicated below. Between absolute refractive index and speed of light in the medium as indicated below. Quickly work. Is a collection of few theories. To be applied. Right. Now look at this. The second theory part. Observe. N1 C1 equals N2 C2. Light is a wave, no? So we can put F lambda 1, F lambda 2. Remember, when the light travels from one medium to another, the frequency will not change. So speed will change means wavelength will change, but frequency won't change. F and F cancel off. These N2, sorry, N1. N1 lambda 1 equals N2 lambda 2. N1 lambda 1 equals N2 lambda 2. From this we can say Nm lambda m is also a constant. Nm lambda m is also a constant. Okay, like that. When light travels from one medium to another, the frequency does not change. The frequency does not change. Only the wavelength will change. Only the wavelength will change. Therefore, the speed will change. Therefore, the speed will change. So N1 lambda 1, N2 lambda N1 C1 equal N2 C2. We can convert to N1 lambda 1 equal N2 lambda 2. That means Nm lambda m is going to be a constant. Nm lambda m is going to be a constant. Right now, Nm lambda m is going to be a constant. Write down. Okay. Right now. Right. Have a look. Then we have relative refractive index. Relative refractive index. Have a look. Let's say here we have medium number 1. Here we have medium number 2. Light is traveling from one medium to another. Light is traveling from one medium to another. So these are you write relative refractive index. Light is traveling from medium 1 to medium 2. You can show the path 1 to 2 or 1 to 2. The way we write this is refractive index of medium 2. Refractive index of medium 2 with respect to medium 1. With respect to medium 1. Refractive index of medium 2 with respect to medium 1. So for example, if I write it, light is traveling from air to glass. This means refractive index of glass with respect to air. If I write this, light is traveling from air to water. Refractive index of water with respect to air. If I write glass to water, this is refractive index of water with respect to glass. There you go. There you go. Basic relationship. Right? Okay then. It's like relative refractive index. Relative refractive index. It's like we can follow the path in which the light travels. We can follow the path in which the light travels. We can follow the path in which the light travels and write a relationship for relative refractive index. And write a relationship for relative refractive index. Write a relationship for relative refractive index as indicated below. As indicated below. Right. Okay, right. Have a look. How do you write this? Refractive index of medium 2 with respect to medium 1. N2 divided by N1. N2 divided by N1. That means refractive index of glass with respect to air is Ng divided by Na. Don't forget refractive index of air is 1. Na is actually 1. Therefore, you can say refractive index of glass with respect to air is Ng. Absolute refractive index of glass. Refractive index of water with respect to air. Nw divided by Na. Na is 1. So we can say Nw here. Refractive index of water with respect to glass. Nw divided by Ng. Very good. So these are you write the absolute or relative refractive index between two mediums. Write the small sentence. We can write a relationship. We can write a relationship for the relative refractive index between two mediums. For the relative refractive index between two mediums, as indicated below. As indicated below. Write down. Quickly write down. right? Okay. Few value problems let's give it. Let's say absolute refractive index of glass 3 over 2. Absolute refractive index of water 4 over 3. So if they give you air to glass Ng over Na 3 over 2 divided by 1, 3 over 2 means 1.5 will come. Okay. Absolute refractive index of water Nw over Na. Nw is 4 over 3, Na is 1.3. Okay. So like this you can keep writing the relative refractive index. Quickly write these two also. Write this one finish. Okay. Okay now. Right. Now look at this. Snell's law. Snell said the sine angle made with the normal when light refracts is directly proportional to the speed of light in the medium. What do you mean by that? Let's say medium 1, let's say medium 2. Light travels from medium 1 to medium 2. Light travels from medium 1 to medium 2. Have a look. Observe this carefully. Here there is angle I, here there is angle R, here speed C1, here speed C2. So what does Snell's law tell you? Sine angle made with the normal directly proportional to the speed of light in that medium. Sine angle made with the normal directly proportional to the speed of light in the medium. If I divide this, sin I divided by sin R, C1 over C2. Simplify this, sin I divided by sin R. Now carefully rearrange this. C over C2 divided by C over C1. Okay, no problem. C cancel off, C1 goes on top. What is C over C2? Absolute refractive index of medium 2. What is C over C1? Absolute refractive index of medium 1. So here you have sin I divided by sin R. Cross multiply. N1 sin I divided by N2 sin R. N1 sin I equals N2 sin R. From that, what you can you learn? Refractive, absolute refractive index in the medium multiplied by sine angle equals absolute refractive index in the medium multiplied by the sine angle. So this relationship is what we get from Snell's law relationship. Right there. Snell's law. Snell's law states that the sine angle made with the normal, is directly proportional to the speed of light in the medium. Is directly proportional to the speed of light in the medium. Is directly proportional to the speed of light in the medium. We can build a relationship. Between the refractive index and the sine angle as indicated below. Between the refractive index and the sine angle as indicated below. Okay. Write down. Okay. Have a look. We'll do a simple example. This is air. This is glass. Light is traveling from air to glass. Angle of incidence 30. They are asking angle of refraction. How will you write this? NA sin 30, NG sin R. Sin 30 is half. NG is 3 over 2 sin R. Sin R is equal to 1 over 3. From this we can find what R is. R is equal to sin inverse 1 over 3. I think it's 19 degrees 28 minutes, something like that. Here, let's say glass, let's say water. Denser medium, rare medium going away. Let's say this is 30, these are. How will you write this? 3 over 2 sin 30, 4 over 3 sin R. 3 over 2 sin 30 is half, 4 over 3 sin R. Simplify this. Sin R is equal to 9 over 16. R is equal to sin inverse 9 over 16. Using the log table, you should be able to find the answer. So, write down. Okay. Right now. Right. Now, so refraction of light, we can use this. Next comes critical angle concept. Critical angle concept. Critical angle concept. What do you mean by this? When light travels from a denser medium to a rarer medium. When light travels from a denser medium to a rarer medium, at one instant, light rays will go along the boundary. When light rays go along the boundary, the angle of incidence is called the critical angle. Angle of incidence is called the critical angle. So here, let's say N1, let's say N2. You can write N1 sin C equals N2 sin 90. N2 sin 90. Sin C is equal to N2 divided by N1. From this C is equal to sin inverse N2 divided by N1, you can find the critical angle. Okay. Let's write when light critical angle topic. When light travels from a denser medium to a rarer medium, when light travels from a denser medium to a rarer medium, at one instant, the light ray will travel along the boundary. The light ray will travel along the boundary. Light ray will travel along the boundary. This is known as the critical angle. The angle of incidence is known as the critical angle. The angle of incidence is known as the critical angle. Right up. Okay. Right. Now remember, whenever there is a refraction, this is something that most people forget. Whenever there is a refraction, whenever there is refraction of light, reflection also occurs. So this is angle I, this is angle R. Remember, these are also angle I. You call this partial reflection. Partial reflection. You can't eliminate it. This partial reflection is always there. These are refracted light, refracted light. So even in the critical angle, there can be reflection taking place. We call this critical reflection. We call this what? Critical reflection. Okay, critical reflection. Right there. Whenever refraction takes place, whenever refraction takes place, whenever refraction takes place, reflection will also occur. Reflection will also occur. We call this partial reflection. We call this partial reflection. Draw, write down. Okay, right. Now, from this we have total internal reflection. Total internal reflection. Now, what do you mean by total internal reflection? If the angle of incidence when light travels from denser medium to a rarer medium, when light travels from a denser medium to a rarer medium, if the angle of incidence is greater than the critical angle, total internal reflection will take place. That means no light ray will go out. Okay, no? That's right. When light rays travel from a denser medium to a rarer medium, when light rays travel from a denser medium to a rarer medium, if the angle of incidence is greater than the critical angle, if the angle of incidence is greater than the critical angle, total internal reflection will take place. Total internal reflection will take place. Right now? Right now. This one. You want this slide? You missed it, quickly write that. Finished? Okay, no? Right. Now look at this. There are many applications connected to this. The famous one, we'll do a few because when you do the questions, you can do the rest. Otherwise, you won't think. Now observe, let's say there's a source here. There's a source here. You're looking from top. So light rays coming from here will directly go into the eye. Light rays coming from here, refraction will take place. Light rays coming from here, refraction will take place. At one instant, light rays will go along the boundary. At one instant, light rays will go along the boundary. And beyond that, if light rays come, total internal reflection only takes place. Total internal reflection only takes place. Beyond this, if light comes, total internal reflection takes place. So we will need to find the radius here. So I'll erase one part because symmetrically it's drawn. I'll erase this one. Here we go. Right. We need to find the radius. We need to find the radius. Here radius, both are same. Both are same. This is the depth. This critical angle means here also critical angle. If I take this the critical angle, here also critical angle. Careful. Now what? Tan C is equal to opposite over adjacent, R over H. So R is equal to H tan C. There you go, radius is formed. What about the area? Area is equal to pi R square. Pi R square is H squared tan squared C. There you go. Is there another way to represent this? Yes. Have a look. Sin C or n sin C equals Na sin 90. Sin C is equal to 1 over n. If you take a right angle triangle here, opposite over hypotenuse, this is n squared minus 1 squared. Wherever there is tan C, we can substitute that. So H tan C is opposite over adjacent. N squared minus 1 squared. N squared minus 1 squared. Okay. So here you go. That's right. Consider source underwater. Consider source underwater. Light rays will refract into air. Light rays will refract into air. And at one instant, light rays will go along the boundary. And at one instant, light rays will go along the boundary. There will be a conical shape path in which light rays come out. There will be a conical shape path in which light rays come out. We can find the radius of that cone as indicated below. We can find the radius of that cone as indicated below. We can find the radius of that cone as indicated below. Quickly draw, prove it. Okay, now, right? Okay. Next one is optical fibers. Now, optical fibers, same. It is used in telecommunication industry mainly. Yeah? Used in telecommunications. It is also used in data transfer, or that's also comes under telecommunication. It's used in lighting and decorations. Used in your touchpad in your phones, touch screen. That also works on this concept of optical fibers or total internal reflection. Mainly it's used in lighting. These things, of course, you can keep it. It comes under that. Right. Now, how does it work? Let's say there's an optical fiber. There. This is called the core. Call this the core. And there can be a coating as well. There can be a coating as well. If I show it here, here you go the core, here you go the coating. So this is the core, this is the coating. Okay. Now what happens is, you must use the ensign theta and work it. Light rays will come from here, some rays will undergo total internal reflection from here. So no light rays escapes out. No light rays escape out. Some of them, even if it escapes, inside the coating, what will happen? Total internal reflection will take place. So the signal never escapes out. The signal is always inside. So this is what optical fibers are famous for. The electrical signal or the light signal never escapes out. Always is inside the fiber. Okay. So when you are doing this, you must use ensign theta, the techniques. Here you must find the critical angle, check and see whether it's more than the critical angle between the mediums. Then total internal reflection takes place. Here if it's less than the critical angle, refraction will occur. Once refraction occurs, this angle, that angle are same geometry. Then you must check whether this angle is greater than the critical angle between the coating and air. Then total internal reflection will take place there. Those are basic things. But for now, you can just concentrate this. Here in the optical fiber, always total internal reflection will take place. Okay, that's right. That's right. In an optical fiber, we use the concept of total internal reflection. We use the concept of total internal reflection. So that the light signal or the data signal, so that the light signal or the electrical signal is also used in electrical systems. Does not escape out of the fiber. Does not escape out of the fiber. Does not escape out of the fiber. Okay. Quickly draw. So now we know total internal reflection. Now we know optical fibers. There's one more special note, then we can quickly discuss that. Then next time when we meet, we can solve the problems and finish. Okay. Okay. Right now? Okay. Have a look. Now, the concept of real depth and apparent depth. Concept of real depth and apparent depth. Look at this carefully. Now, if you consider an object at the bottom here, and you are looking at near normal incidence from here, light rays will directly go into the eye. And remember, whatever I draw here actually is entering the eye. Yeah? So this angle is very, very small. This angle is very, very small. Look at this carefully. These rays also enter the eye. Therefore, the image is formed here. Look at this carefully. This is your real depth. Like, if this angle is I, this angle is also I. If this angle is R, this angle is also R. Here you have A, here you have B. I, R are very small. They're very small. If they are very small, sin I is approximately tan I. Tan I is opposite of adjacent AB divided by OA. Also, sin R is approximately tan R. Tan R is opposite of adjacent is AI. Now, if you write the relationship here very carefully, N sin I is equal to NA sin R, sorry. Sin I is equal to AB over OA. Sin R is equal to AB over AI. AB cancel off. OA divided by AI. What is OA divided by AI? Real depth divided by apparent depth. Real depth divided by apparent depth. Look at this carefully. What do you call this distance? This is called the apparent shift. This is called the apparent shift. So if I write it from here, apparent shift is equal to OA minus AI. What is AI? AI is OA divided by N. Take OA out, 1 minus 1 over N. So you can write apparent shift is equal to real depth 1 minus 1 over refractive index. Right? 1 minus 1 over refractive index. Okay. Right there. At near normal incidence, for light rays to enter the eye, for refracted light rays to enter the eye, for refracted light rays to enter the eye, simple I R should be very small. Simple I and R should be very small. Angle simple I and simple R should be very small. We can find the relationship between the refractive index. We can find the relationship for the refractive index and the apparent shift. We can find the relationship for the refractive index and the apparent shift in terms of real depth and apparent depth. In terms of real depth and apparent depth as indicated below. in terms of real depth and apparent depth as indicated below. Okay, right now. Okay, right. Now, even if there is multiple mediums, or if you, let's say, keep the object slightly below somewhere here, the image location will be different. Rarer, denser towards the normal, denser, rarer away from the normal. The image location will be different. Like the object is here, O dash, image will be I dash. If the object is O, image is at I. Look at this carefully. So even if you keep this x distance below, the apparent shift does not depend on this distance. I'll show it to you. O dash is parallel to I dash. Also OI is parallel to O dash I dash. So O dash I is a parallelogram. If it is a parallelogram, OI is equal to O dash I dash. What does that mean? Apparent shift when object at O equals apparent shift when object at O dash. So what can you conclude? Therefore, apparent shift does not depend on x, how far it is from the medium. Okay, right there. We can show that the apparent shift is independent of the distance x. We can show that the apparent shift is independent of the distance x. So if we keep an object far below a medium, the apparent shift is same as keeping the object at the bottom of the medium. Okay, no? So from this, actually, we can, I'll show that also. We can move to multiple mediums, which is the last part. Let's say there are multiple mediums. Here T1, here T2, here T3, here absolute N1, N2, N3. I'm keeping object here. So the total apparent shift is the sum of the apparent shifts from each medium. Sum of the apparent shifts from each medium. Here T1, N1. Here T2, N2. Here T3, N3. So we can write total apparent shift. Is going to be the sum of the apparent shifts from each medium. 1 over 1 minus 1 over N1 plus N2 1 over 1 minus N2 plus N3 1 minus 1 over N3. Because it's not dependent on this distance. Does not depend on that distance. Okay, right. That is more sentence there. We can also show that if there are multiple mediums, the total apparent shift is independent of. The total apparent shift is independent of the distance from the object to each medium. The distance from the object to each medium. The distance from the object to each medium. Distance from the object to each medium. It is the scalar sum. It is the scalar sum. It is the scalar sum of the individual apparent shifts in each medium. Of the individual apparent shifts in each medium. Scalar sum of the individual apparent shifts in each medium. Okay. We'll go back to earlier one. Earlier one, prove it, then you can write this. Okay now? Right. Just to finish it off, have a look. Now we did this comparing with air. What if this was a different medium? This was a different medium where you keep your eye. Look at this carefully. Object is here, light ray goes in. Extend it backwards here, I means here I, here R means here R. Here AB, this is I. To simplify it, IR very small, sin I approximately tan I, opposite to adjacent ABOOA. Sin R approximately tan R, ABOAI. To write the equation, N2 sin I equal N1 sin R, N2 sin I is ABOOA, AB over AI. AB cancel off. N2 over NA is OA over AI. Real depth over apparent depth. What is N2 over N? Rarer with respect to denser. So relative refractive index. Now light is going from 1 to 2, but this is from light is going from 2 to 1. But here, there you refractive index of denser medium with respect to rarer medium. Refractive index of denser medium with respect to rarer medium is always what real depth over apparent depth. Refractive index of denser medium with respect to rarer medium is real depth over apparent depth. Don't forget. So if there's a different medium there, don't panic. You have to find the refractive index of the denser medium with respect to the rarer medium. That's right. If there is another medium except air, if there is another medium except air, when we write the real depth apparent depth relationship, we consider refractive index of denser medium with respect to the rarer medium. We consider refractive index of denser medium with respect to rarer medium. We consider refractive index of denser medium with respect to rarer medium as indicated below. As indicated below. Here itself we can finish the apparent shift part. So the apparent shift at once we can finish it. That is equal to OA minus AI. OA minus AI means OA over refractive index of denser medium with respect to rarer medium. OA 1 minus 1 over there you apparent shift. Real depth 1 minus 1 over refractive index of denser medium with respect to rarer medium. Okay, right. Write it. Okay. So always remember, if they by any chance give a different medium except air, what should come here is refractive index of denser medium with respect to rarer medium. And in the apparent shift equation also say refractive index of denser medium with respect to rarer medium. Okay. Right. So the section revision for this part is done. So when we meet in the theory revision class, you can solve the problems and then. Okay. Okay. Stay home safe.